Welcome back to section 2.3, and the next thing that we're going to look at here is the idea of proving limit statements. And this is something that we have to use this new formal epsilon delta definition for. So in proving limit statements, using limit tricks is not enough to solve this type of problem. We have to use that formal definition. Okay, so a proof type of problem, a proving limit statement problem, will look something like this example right here. It will say something like, prove that the limit as x approaches some value of a certain function equals a certain number. Okay, now this problem here, proving that the limit as x approaches 4 of 2x plus 3 equals 11, we can tell pretty darn quickly that that is a true statement. We know that that limit is actually 11 if we just do a little direct substitution really quickly. Plugging in x equals 4 into our function here, you'd get 2 times 4 is 8 plus 3 gives us 11. So using a limit trick like that is not enough to do this type of problem. It doesn't say calculate the limit or find the limit. It says prove that this limit is actually what we're saying it is. There's a big difference between finding something and proving that something is true. Okay, so we need to use this formal definition. Now, when we do proof problems like this, you might find if you go further into more mathematics classes, you start doing more proofs, and there are some formalities to this type of problem. They're a little bit wordy. Sometimes you have to use fairly specific language. One thing that we're going to start all of these proofs with is the statement, let epsilon be given. And what that's saying is in this proof problem, we are saying, okay, we can be given some generic sort of epsilon value. In the previous couple of examples, we've known a specific epsilon. Now in these proofs, we're saying, okay, epsilon doesn't necessarily have to be just one particular value. You could give us any epsilon you want, some generic epsilon value, and we're going to be able to find a delta to go with that generic epsilon. Okay, so that's why we're going to start our proofs with let epsilon be given. It says, okay, give us this generic epsilon. We're going to prove this thing. And then to start using our formal definition, we're going to essentially write the formal definition. The absolute value of f of x minus L is less than epsilon when the absolute value of x minus c is less than delta. Okay, that is our formal definition of a limit. And we're going to write that down and then put in whatever we know from those statements. So perhaps in your problem, you know what f of x is. Maybe you know what L is. Maybe you have a C value. You could put those things into those statements and it's going to help the process of the proof. Okay, and then once we've done that, we can start with one of these inequalities. We're going to start with absolute value of f of x minus L is less than epsilon. We're starting over here. And we're going to work with that until we get this other part of the formal definition to pop out, essentially, to show up in our problem. Okay, we're going to start with this epsilon statement, and then we're going to manipulate that inequality, okay, manipulate the absolute value statement until you eventually see the form of absolute value x minus c. Okay, we'll do some examples here. You'll see how this is going to work out. Okay, once you see that absolute value of x minus c, it is still going to be in an inequality statement, okay? So it's gonna still be less than something. So that something, when we see absolute value of x minus c come out, that is going to be less than delta. So that's going to essentially find your delta value to go with the generic epsilon that we were given. Okay, and that's the last step here, to choose delta in terms of epsilon to make the statements hold true. Okay, so how does this prove the limit statement? All right, I briefly touched on this a little while ago, but we're essentially saying with let epsilon be given that someone, anyone, the powers that be, okay, could give us absolutely any epsilon, even just the tiniest epsilon value. And remember, epsilon is the difference between your function values and the limit that we're supposing, okay? So epsilon makes that tiny interval around L along the y direction. So having a very tiny epsilon value, any super small generic epsilon, means we're getting very close to that limit, as close as this mystery person wants us to be. Okay, so given absolutely any epsilon, we can find the corresponding delta to go with that. So we can essentially determine, okay, how close do we need to be to x equals c in order to make sure that we fall within that specified range along the y direction. Okay, it's essentially like proving these statements is kind of like saying, okay, challenge accepted. You're gonna give me an epsilon, whatever it is, I'm gonna find you a delta to go with it. I can find it regardless. So as long as we're within delta of x equals c, we're guaranteed to be within epsilon of that limit value. So we take on the challenge, we manipulate our formal definition statements, and we are eventually going to get to choose delta in terms of epsilon to make these statements hold true. So let's see how this works. We are going to prove that the limit as x approaches 4 of 2x plus 3 equals 11. Okay, so what we're going to start with is let epsilon be given. We are literally going to write that statement. Okay, let epsilon be given. Okay, so that is essentially the part that says, challenge accepted. You are giving me this epsilon, and I, in the course of the next couple parts of this proof, I am going to find you a delta to go with that epsilon. Guaranteed. Okay, so then we will write our limit definition. You can write the generic version first if you'd like. Absolute value of f of x minus L is less than epsilon when absolute value of x minus c is less than delta. Okay, now we are going to plug in the information that we've been given in this problem. Okay, let's take this right over here. And we know what f of x is in this problem. It's right here. It's the function that we're taking the limit of. F of x is 2x plus 3. We know what L is. It's the limit value itself. L is 11. And we also know what C is. C is down here. X approaches C, so our C value is 4. Okay, so we're going to put these different things in. All right. x minus c, that's going to look like x minus 4 in the absolute value is less than delta. Okay, and then absolute value of f of x minus L less than epsilon would look like this. Absolute value of f of x, that's 2x plus 3, minus L, which is 11, absolute value, is less than epsilon. And note that we do not have a specific epsilon here. We don't know the value because we said we were going to let epsilon be given to us by a mystery person. Okay, so what we're going to do here is start manipulating this f of x minus L statement, okay? We're going to manipulate that until we start seeing something that looks like x minus c show up. Okay, if we combine some like terms here, we're going to have 2x minus 8 inside that absolute value, which can be factored. 2 times x minus 4. And you might kind of start seeing a little something here. Notice how x minus c is x minus 4. That's starting to show up, but it has this 2 still stuck inside there. We are looking to just have absolute value of x minus 4 by itself. Okay, so we are going to split our absolute value here. Absolute value of 2 times the absolute value of x minus 4 less than epsilon. Okay, and absolute value of 2 is 2. All right, so now we have 2, absolute value of x minus 4 less than epsilon. Let me curve this up here, and we'll divide by 2 on both sides. So then the absolute value of x minus 4 is less than epsilon over 2. Okay, so that is where this absolute value of x minus 4 statement appears. Okay, we see the form of absolute value x minus c. So it should be less than delta. So there's the less than. This right here is going to be our delta. Okay, so notice that it says we are going to be choosing delta in terms of epsilon. So epsilon is a part of our delta here. All right, so that is going to make our delta. We say, therefore, to finish this proof, we are going to choose to use the delta of epsilon over 2. All right, and that will do it. Okay, so in practical terms, what this is saying is if someone gave us an epsilon, like one of our previous problems, let's say they gave us an epsilon value of 0.02, okay, a pretty small epsilon there. We automatically know now, after doing this proof, we instantly can tell them what the delta needs to be to go with that epsilon. If they told us epsilon is 0.02, okay, we're going to say, all right, your delta is that epsilon divided by 2. So your delta is 0.01. That was fast. We didn't have to go through a graphing process. We didn't have to go through a full algebraic manipulation again. Now that we've completed this proof process and we have a generic delta in terms of epsilon, we're able to find corresponding deltas very, very quickly. All right. If they told us epsilon was 0.0001, okay, or any value like that, to find the delta to go with it, you would just cut that epsilon in half, and that would be your delta. So we've proved that this limit truly is what we say it is. That limit of 2x plus 3 as x approaches 4 really is 11, because no matter how small the epsilon is, we know the delta that's going to go with it to ensure that we fall within epsilon of that limit value.